In this podcast, we're going to be studying solving linear equations. We're actually going to go a little bit further than that. We'll not just solve linear equations, but we will solve equations which become linear after the fractions are removed. Some of these are not technically linear when we start the process, but they are after the first step. Okay, let's go over what I call the five-step method for solving linear equations. Since there are 5 steps, that's kind of a lot to remember, but if you'll go through every one of the 5 steps, every time you work a problem, whether you need the step or not, by the time you've finished your homework, you'll be doing all 5 steps automatically. That is, you'll have memorized them without even trying to. So as I go through these, I'm going to go through every one of the steps every time. Make sure you put these steps on your notes so that once we leave this page, you'll still have the 5 steps beside you, or just put your 5-step sheet from your notebook right beside your homework page now so you can refer to it as you go through the problems. Okay, let's begin. Number one has a fraction in it. Step 1 says eliminate fractions, multiply every term by the common denominator. This equation has 2 terms and they are separated by the equal sign. Remember, terms are separated by plus signs, minus signs, and equal signs. There are no plus or minus signs, so this is a 2-term expression. And it says multiply every term by the common denominator. Normally you'd have to stop and figure out what the common denominator is at this point, but we only have one denominator, and that's 3, so that's the common denominator. So I'll multiply this first term by 3 and the second term by 3. Now the reason that you're doing that is to eliminate fractions. That's your first step, eliminate fractions. So let's cancel, and that eliminates our fractions. On the other side, we have 12 times 3 is 36. Problem done, and we're on to number 2. Again, I see a fraction, but this time only one fraction. Again, the common denominator is 3, just as before. But remember that says multiply every term, and I put that in capital letters, every term by the common denominator. So even though the 5 doesn't have a denominator and the 7 doesn't have a denominator, those are terms. These first 2 terms, this piece and the 5, are separated by a minus, so that's 2 terms on the left, and then the 7 is separated from the 5 by the equal, so that's another term on the right. So that's 3 terms, so 3 times I'm going to have to multiply by 3. Now go ahead and write that out. I know that you'd rather take shortcuts and not go through all the work, but go through the work and write it out. You're going to multiply that first term, so put it in a bracket, and multiply it by 3. Multiply the second term by 3, and then multiply the third term by 3. Every term, whether it's a fraction or not, gets multiplied by the common denominator. Now remember, the purpose is to get rid of fractions, so immediately cancel your 3's. Now, think about what you have left. Your first term is negative 2 times x minus 3. Your second step says get the objective variable out of the grouping symbol, and it says to do it by distributing. Well, if I distribute the negative 2, I'll get negative 2x, and then negative 2 times the negative 3, plus 6, minus 3 times 5, which is 15, is equal to 3 times 7, which is 21. And notice that I have gotten rid of all of my fractions, and in a second step, by distributing the negative 2, I've gotten my objective variable out of the grouping symbol. Now, every time you can, stop and simplify. I put that up here kind of off to the side. It's not technically one of the 5 steps, but if you can make your work simpler, keep it simple. Here I have 6 minus 15. I can simplify that. So I get negative 2x minus 9 equals 21. Now notice a pattern that I'm making. My equal signs are coming straight down. And in every step I have a number on the right and a number on the left. I never leave either side blank. Even if what's on one side is a 0, I put a 0 there because I always want a number on the right and a number on the left. Let's go on to step 3. Step 3 says get all your x terms to one side. Well, I only have one x term. It's right here and it's on the left, so I've already done that. But step 3 goes on with a capital AND. Get all your non-x terms to the other side. Well, if my x term is going to be on the left, then I want this 9 on the right. So I add 9. And I get negative 2x on the left is equal to 30 on the right. Next step says form a single x term. That means one x term. Well, one x term is all I've got, so I can just skip over step 4. In step 5, reverse the last thing done to x. The only thing done to x is that it's multiplied by negative 2, so to reverse that I divide by negative 2. The negative 2's cancel, and I get x equals negative 15. Problem done. On to the next example. Example 3 has no fractions, so I do not have to eliminate fractions by multiplying every term by the common denominator. In fact, since there aren't any denominators other than 1, the common denominator is just 1, so multiplying every term by 1 wouldn't change anything anyway. So let's go on to step 2 that says get the objective variable out of grouping symbols by distributing. Right here on this left side, a lot of people are going to be tempted to call this 8 times 2x plus 1. But recall the order of operations. In the order of operations, multiplying comes before adding, and this 3 is multiplied by the bracket. You've got to do that before you add 5. The multiplication must come first. If you do 5 plus 3, you're violating the order of operations. Okay, so I'm going to distribute this 3. That's also going to get my x out of the grouping symbol, which is step 2. Get the objective variable out of the grouping symbol by distributing. On the other side, I've also got x in a grouping symbol, but what do I distribute? There's no number there. Well, recall that all numbers are always multiplied by 1, so there's an invisible 1 right here. So I'll show it with kind of a ghost-looking 1 there. Okay, let's proceed. We're going to get x out of the grouping symbol. We get our 5 plus 3 times 2x is 6x. 3 times negative 1 is negative 3. On the other side, 3. Now here's what you do. I'm only going to show this once. This is kind of a mental thing that goes on. Right now this says minus positive 1 times. You can change two signs if they're right together. So mentally, we change this to a plus, so I'll make a little ghost plus negative 1 times x plus 3. In other words, we look at this as being a negative 1 rather than a minus positive 1. So as I distribute a negative 1 to my two terms, I get negative x minus 3. Now again, anytime I get a chance, I'm going to simplify. On the left, I have 5 plus negative 3. Well, that's just 2, so I just change it to 6x plus 2. On the left, the negative 3 added to the positive 3 zeroes out, so I'm left with just negative x. And we have completed step 2, get the objective variable out of the grouping symbol. Step 3 says get all your x terms to one side. Notice right now my x terms are on two sides. So what I'm going to do is get the x off of one side by adding x. I bring my equal sign straight down as always, and on the right side, negative x and positive x zero each other out. I don't leave that blank. I put a 0 there. I always want a number on the right and a number on the left, which would be 7x plus 2. But step 3 goes on with the big capital and it says and get all your non-x terms to the other side. So I'm going to take my 2 to the other side, minus 2 minus 2, and now I have 7x is equal to negative 2. I'm now going to move this up for space sakes. I'm just going to recopy it. I don't want to move it and change it at the same time. That would probably make me have a mistake. So I go down to step 4. Step 4 says form a single x term. Again, this is already a single x term, so we don't really need to do that. Let's go on to step 5, which says reverse the last thing done to x. The only thing done to x is it's multiplied by 7. To reverse that, you divide by 7. Always pay a lot of attention to what is done to x, and make sure you're reversing what is done to x. I cancel the 7's and I get x equals negative 2/7. That is a perfectly good simplified answer, so I stop there. Let me go back to that last step again. It says reverse the last thing done to x. Always think in terms of that. A lot of people, if you go back to example 1, a lot of people, when they say x over 3 equals 12, they're not even going to do a step. They're just going to say, oh, well, I'm dividing by 3, there's a 12, so x is equal to 4. Don't fall into that trap. Think about what is done to x. Focus on x. X is divided by 3. To reverse that, multiply by 3. And then you'll avoid that trap, and you get x equals 36, not x equals 4. Okay, let's move on to another one. Now this one you might recognize as a proportion problem from your high school days. And a lot of people solve proportions by cross multiplying. I don't have a problem with that. If you do it correctly, you could just cross multiply to solve for x. But I'm going to stick with my 5 basic steps. And my first step says, get rid of your fractions by multiplying every term by the common denominator. When you only have a couple of denominators, and it's not clear what the common denominator is, then for the common denominator, just multiply the denominators together. So for my common denominator, I'm going to use 7.3 times 6.5. And I'm going to multiply each term by that. So 7.3 times 6.5 times the left term, x minus 2 over 7.3, is equal to 7.3 times 6.5 times the second term. And if you'd rather put this on the right side of the second term, that's okay. Doesn't matter. Multiplication is commutative. I can put this on the left of the term or I can put it on the right of the term, and it will make absolutely no difference at all. So the next thing I do is to get rid of fractions, I cancel. Here I cancel the 7.3 with a 7.3. Here I cancel the 6.5 with the 6.5. And I end up with 6.5 times x minus 2 is equal to 7.3 times x. Now, we're running out of space, so I'm going to go to the next page to finish this up. But I have to be careful. I don't want to go too far to the next page to finish this up. Let me bring some of the other page back in here so we can see it. Okay, the next step says get your x terms to one side and your non-x terms to the other, and I have two choices here. I could move the 7.3x to the left, and I could move the negative 2 to the right, or I could just move the 6.5 to the right. That's what I'm going to do. That will do my job in one move instead of two moves. And also I'm using kind of a rule of thumb here. When there's two x's and I'm trying to decide which side to move x to, I pick on the little guy. Here 6.5 is littler than 7.3. That's the one I'm going to get rid of. So minus 6.5x minus 6.5x. And on the left I have negative 2, and on the right I have positive 0.8x. I now divide both sides by positive 0.8. And I get x is equal to negative 2 over positive 0.8. There's a couple of ways to finish here, but you have access to a calculator. So I would just go ahead and do that on a calculator. Negative 2 divided by positive 0.8. And what you get is negative 2.5. And you'll have your calculator with you during a test, so you can always count on that. Let's go on to the last one. Now, in the last one, we get a more complicated denominator. This is the type you might see in section 6.8, where the problems get a tad more complicated. And here it's worth looking for that common denominator. Recall what we call the European method. We line up all our denominators, 3r, 5, and 15r. We ask ourselves, is there a number that will divide more than one of these three numbers? Well, clearly 5 will, so we divide by 5. Now 5 doesn't divide evenly into 3r, so we just bring it down. 5 does go into 5 one time, and 5 goes into 15r 3r times. And we ask ourselves, is there any number that would divide more than one of these? Well, it looks like 3r is certainly going to divide more than one of them, so I'm going to divide by 3r. 3r goes into 3r once. 3r doesn't divide into 1, so I just bring it down. And 3r goes into 3r once. We take our outside L-shaped bracket. We multiply all the numbers together. 1 times 1 times 1 times 3r times 5. And we get that the common denominator is 15r. So I need to multiply every term by the common denominator. So I multiply 15r times the first term minus 15r times the second term is equal to 15r times the third term. And now when I cancel, if I've properly chosen my common denominator, I will have no fractions. Well, the 3 on the bottom cancels the 3 in the 15, but doesn't cancel the 5 in the 15. So the 5 is still there. The r on the bottom cancels the r on the top. In the second one, the 5 on the bottom cancels the 5 in the 15, but it doesn't cancel the 3 in the 15. And on the last one, the 15r cancels the 15r. So I end up with everything here is canceled except the 5. Everything here is canceled except the 3 times r times 2, so I say minus 6r. And over here, everything canceled except the 8. Wow! Did that simplify the process? The second thing we would do is get r out of the grouping symbol, but r is not in a grouping symbol. So we go on to step 3 that says, get your r terms on one side, your non-r terms on the other side. Well, my r terms are already on one side. They're on the left side. But this 5 is a non-r term, so it has to go to the other side, so I say minus 5, minus 5. And I get negative 6r is equal to 3. Remember, I'm doing a 5 minus 5 here, so that's 0 minus 6r, which is negative 6r, and then 8 minus 5 here, which is 3. The next step says form a single r term. Again, that is a single r term. A single r term just means one r term, and that is one r term. And the last step says reverse what is done to r. Again, emphasize strongly in your own mind what is done to r. r is multiplied. It's multiplied by negative 6. To reverse that, divide by negative 6. The negative 6 on the left cancels, and I get r equals negative 1/2, and that completes the first podcast on linear equations. In the second podcast, we're going to go into something called literal equations, where there's more than one variable in an equation, and that concludes our podcast.